let's start. So, well, thank you very much first for the invitation to come to beautiful but cold Paris these days. So it's a pleasure to be here to talk to you about biomineralization. We'll have a slight problem with the format of the presentation, as this morning I was told, so it's a little bit distorted, but that's what we have to live with today. So I would like to talk to you about some peculiar properties of biominerals. I think that's a title which Thibaut Corradin proposed, so I'll try to do my best to stick to it. So this is a number of examples on biomineralization, biomineralized tissues, which we investigated in the last 10 years or so together with people from biology, mainly with high-end chemical and physicochemical methods, like mollusk shells, cuticles of woodlice, statoliths of deep-sea medusa, shark teeth, and crocodile teeth. But of course there will be questions and answers at the end as well. Okay, first, where I come from, this is Paris. This is Essen University, which is here, so on the northwestern part of Germany, just to give you an idea where my university is. And I would like to present you these topics I've shown you. And we will start with the formation of mollusk shells. That's a topic which I've seen at the posters and the program, which is very prominent, of course, in biomineralization. And this is a collaboration project we had with biologists from Hamburg University, from zoology. We studied the shell of the freshwater snail Biomphallaria glabrata, which consists of calcium carbonate, as most mollusk shells do, as you know. We did synchrotron X-ray powder diffraction, and we found that the shell consists of aragonite plus traces of vaterite, less than 1%. We could quantify this. With synchrotron X-ray powder diffraction, you can go down to maybe 0.05 weight% of another polymorph. Well, at the end, we never found out what the reason for this 1% of vaterite is. But just as an example, what you can do with high-end solid-state chemical methods in biomineralization. So we did X-ray powder diffraction at the synchrotron. So you have a very good signal-to-noise ratio. Then you can do Rietveld analysis to make a quantitative analysis of this powder diffractogram. Then you can quantify the amount of aragonite and vaterite down to about 0.05 weight% of the other polymorph. And there's a good reason to go to a synchrotron, and of course there are synchrotrons in France or in Europe as well, like ESRF, you know. And just for comparison, what you can do with a lab instrument for powder diffraction. So this is a normal powder diffraction scan for such a sample with a laboratory instrument. And this is with a synchrotron X-ray powder diffraction setup. You can see the signal-to-noise ratio is much better because you have a much higher number of photons. And of course, the signal-to-noise ratio is much better. If you look on the red curve, labs instrument, and black curve, synchrotron powder diffractometer, you can see that you can detect small impurities or other polymorphs with a very high degree of sensitivity. Yep. Well, we studied the formation of the shell of Biomphallaria glabrata, and our questions were: how does the shell form? In which polymorph, aragonite, vaterite, or amorphous calcium carbonate? You have heard something from Mr. Gebauer this morning, also during the conference. You will hear more, I believe. So which crystalline or amorphous calcium carbonate polymorph? When does it start to crystallize? And for this we investigated embryonic snails in which the cell was just forming. So this is only possible if you work together with biologists, of course. So these are larvae of this freshwater snail, Biomphallaria glabrata, taken out of the egg after, well, 48 hours after oviposition, after the egg was laid. So 48 hours, 60 hours, you see how the shell starts to form here, more or less. It's not very hard, it's not highly mineralized, obviously, but here after 72 hours you can see the shell, how it is formed. It has some stiffness. 96 hours, the shell is harder, and at 122 hours, shortly before hatching, you can see the crystalline shell of the embryo. So the colleagues from biology undertook the hard work to collecting several hundreds of embryos. Of course, you cannot do analysis of one embryo, at least not with powder diffraction or other analytical techniques. So they collected several hundreds of embryos with a given age and gave us these samples. And what we did was first X-ray powder diffraction at the synchrotron with a high resolution, a high signal-to-noise ratio. This is an adult snail with aragonite. This is 140 hours, so shortly after hatching. You see the crystalline phase of aragonite in this sample, which also contains a lot of biological material, of course. And after the 72-hour sample, where we already have seen the shell, more or less mineralized, there's absolutely no crystalline material present. So it's absolutely X-ray amorphous. But in the scanning electron microscope, we could see something like a solid shell. So in this case, X-ray diffraction could not help us. Then as a chemist or as an analytical person, you have a problem because we typically rely on X-ray diffraction to analyze mineralized samples. If the samples are X-ray amorphous, the number of techniques is limited. You can do solid state NMR, but for calcium and carbonate, so it's not really the technique of choice. And have all this organic material around. Infrared spectroscopy also does not work because there's so much organic material present. And another method has to be applied. And that's a technique. So we did these experiments now maybe 10 years ago. At this time, XRF's X-ray absorption spectroscopy was a rather new technique, especially in biomineralization. Now people have become used to it. A number of people have used X-ray absorption spectroscopy. XRFs, we don't want to go into details of the method because it's a physical method which takes some time to explain. We will just look on the results. With XRFs, you can, at the synchrotron, study the radial distribution of other atoms around one specific element. And this was calcium XRFs. That means all calcium atoms in the sample are at 0. And then you have some next nearest neighbor distribution for other atoms in a distance from the calcium on the angstrom scale. Here you can see the oxygens around the calcium, and then you can compare this to the other crystalline phases and then make some conclusions or some deductions about the nature of this phase. The advantage of XRFs is it works with crystalline phases, and it also works with amorphous or X-ray amorphous phases. It even works with liquid phases or glassy phases. It works with everything. That's the advantage of this method. So this is aragonite. If you have a crystalline sample and you do XRFs, you can identify the shells by crystallography around the calcium atoms. The first shell is oxygen, then we have some carbon shells, then we have a prominent calcium-calcium shell. Now we can compare this to our samples from the embryonic snails. 72 hours, completely X-ray amorphous, but you still already see some short-range order around calcium, probably some oxygen sphere. If you are doing a quantitative evaluation, you can see that this is really oxygen in the environment of the calcium. 140 hours, so shortly before or after oviposition, after hatching, you can see a more prominent shell, so the long-range order appears to increase. The crystallinity has increased. Now, what we did, we made a quantitative evaluation, and then you can determine the distance between the calcium at 0 and the neighbors. And the first shell is calcium oxygen. And then you can compare the embryonic snail data to the crystalline polymorphs like calcite, vaterite, aragonite. And you can see that it's maybe aragonite, but it's definitely not calcite because the oxygen atoms are too far away from the calcium to be calcite. If you look on the prominent calcium-calcium shell, which is present in all these polymorphs, you can again compare the embryonic snail shells to the crystalline polymorphs. So it's not vaterite because it's too close to the calcium. So it's maybe aragonite or calcite, but we have excluded calcite. Therefore, we think, if you want to argument on a crystallographic basis, that the aragonitic structure of calcium carbonate is already imprinted into these X-ray amorphous calcium carbonate shells, which makes sense, of course, because the crystalline shell at the end is also aragonite. So it makes sense to assume that this X-ray amorphous calcium carbonate already has some aragonitic short-range structure. Short range, but not long range. So imprinted, which is close to the work of Mr. Gebauer, who thinks or believes and has shown that crystallizing minerals already have their structure imprinted even when they are still X-ray amorphous. Okay, this summarizes what I've just said here. So aragonite short-range order implies the crystallization later to crystalline aragonite. Now, if we look on the structure a little bit more, this was crystallography, now we look on the structure. If you want to analyze the structure of a growing snail shell by scanning electron microscopy, of course you can take such an object, an embryo, take it out of the egg and cut it open with tweezers. It's a very sensitive work, but it's possible. And then you can have a scanning electron micrograph and you can look on the shell. The problem is you always see the shell and all this organic material inside the snail as well. And it's very difficult to dissect such an embryo which is only a few hundred micrometers large. So biologists can do this. I could not do this. So again, this picture, this was the large one. If you want to go to these small ones and try to dissect something, it's a very, very tedious thing. So what we did was microcomputer tomography. That's a technique which is now almost standard at synchrotron radiation sources, and you can also get lab source instruments to buy. It's based on the absorption of X-rays by, well, X-ray dense matter, like hard tissue, like bone or teeth. That's what you do if you go to a doctor after you have broken your leg. He will take an X-ray image, like a transmission image, and your bones will show up and the soft tissue will be more or less transparent. That's how X-ray analysis works in medicine. Now, if you want to have a better image, a three-dimensional image, you can do microcomputer tomography, and with the advent of better radiation sources and faster computers, it's now more or less standard, well, in medicine, but also in materials research, including biomineralization. The idea is you have some X-rays coming here from the synchrotron or from the lab instrument, and you make a projection of an object which has got some X-ray dense and some X-ray transparent sections or parts or voxels. X-ray dense means mineralized, X-ray transparent means soft tissue and everything else. And the X-ray absorption contrast is very high between hard tissue and soft tissue. You can really distinguish this in a two-dimensional image. And the idea is to collect a number of these images, a couple of hundreds, by turning the object into all these three dimensions, and then reassembling all these two-dimensional data into a three-dimensional data set. That's now routine. So you need a fast computer and some gigabytes for data sets, but that's routine nowadays. And then you can have a three-dimensional object where the hard tissue shows up as, well, black voxels, for instance, and the soft tissue is just transparent. That means absent. And that's a typical synchrotron micro-CT image of an embryo or a small snail of Bionfalaria glabrata, where the whole soft tissue is still present. There was no dissection or preparation or oxidizing or something. We took the whole animal, it's embedded into resin, which is also X-ray transparent. You make a micro-CT image, a three-dimensional data set, then you can see the shell and nothing else. All the soft tissue is still inside the object. And then you have this data set, you can make cuts and turn it. I'll also show you a movie in a minute. Then you can have a look on the shell inside, buried under this soft tissue. That's a very convenient technique in biomineralization, because typically in biomineralization we have hard tissue and soft tissue. That means high X-ray contrast and low X-ray contrast. So for biomineralization, I think it's a very convenient technique. So now I would like to show you one movie. As soon as you've got this data set, you can make a movie out of it. So this is one of these snail embryos with all the soft tissue inside, remember. But we don't see it because it's X-ray transparent. Then you can turn it and go through it and cut it. So that was one about turning, now one about cutting. So you can look inside where the the shell has formed. Yeah. And if you look on it from the viewpoint of biology, the shell forms, it starts at the inside, and the snail adds more and more turns when it is growing. So if this snail is growing, the new shell is added here and adds more and more turns when it grows. So the oldest part of the shell is inside, that's the youngest part of the shell. Well, then you can make some quantitative analysis. The voxel size in micro-CT at the synchrotron is typically 1 micrometer approximately. And then you can measure the thickness of the shell. So it's thin at the beginning and becomes thicker. And here, where the new shell is formed, it is still thinner and waits to become thicker in the terms during the biological growth. Well, then you can compare embryos of different age, here all with the same scale bar. How the shell grows becomes more and more ordered. You can compare it to scanning electron micrographs, and the advantage again is that you are cutting out all the soft tissue. You see only the hard tissue, the shell. Yeah, one interesting thing to see was this is a more or less adult, or not, a juvenile snail, 5 days after hatching, 1 millimeter, so you can really see it. If you make a micro-CT image and you cut it and look inside, you can see some X-ray dense material. These are small parts of sand or stones or something which the snail is typically eating, and that's part of this, or inside the stomach of the snail. That's normal, that's a biologist, that's what the biologists have told us. They eat some inorganic material to better cut or chew the nutritionals, and that's still in the stomach. We could really see it inside the stomach in this juvenile snail. Also in the adult snail, you can see it again here, this inorganic material. So it's a very valuable technique to study mineralized tissues, and as a rule of thumb, the resolution is about 1 micrometer if you have a sample which has a dimension of about 1 millimeter. So it's about 1/1000th of the dimension of the object, which gives you 1 billion data points, or 1 billion voxel points, which is a large data set. But the resolution is about 1 micron, not smaller than that. Well, then you can do more quantitative analysis. You can compute the weight of the forming shell. You can take the voxels, which are mineralized. Your volume per voxel is known from the geometric setup. You can compute the volume of the shell and also compute the weight of aragonite if you put into this the density of aragonite as an approximation. And then you can see how the shell is growing when the animal is becoming older. Here it's hatching, oviposition and hatching. That's not possible with normal techniques because you could not, by elemental analysis, distinguish between inorganic calcium, for instance, and organic calcium somewhere else in the soft tissue. Okay, the next example is the biomineralization in crustacea or woodlice. This is a normal or common woodlouse, as it is found in Germany and in France probably as well. These are the woodlice which you find in your garden below some rocks or so. These, a normal woodlouse. I learned from the colleagues from biology that woodlice are very successful in evolution, much more successful than humans. They have been on Earth, I don't remember, since 100 million years or so, and they will probably be here when all humankind has died. So they're very successful, and there are several thousands of different species worldwide of woodlice. So not only these ones in our garden, there are many, many more. The interesting thing is that they have a cuticle, they have an exoskeleton. Humans have an endoskeleton. Our bones are inside. In this case, in crustacea, the skeleton is on the outside. And what we see here is not an optical photograph, it's a synchrotron micro-CT image. So we see only the mineralized parts of the animal. The cuticle is mineralized. It contains calcium carbonate, as we will see in a minute. We can also make a cut through this object. We see that this whole animal has an exoskeleton including the eyes and even the tail and the legs and everything, and these tentacles. So it's fully mineralized on the outside. There's no open pore or something, at least not on this length scale. If you look from below, you can see the legs and the tail. And then you can make nice movies. Now we'll cut it open. Look inside. So inside there's nothing, only soft tissue, nothing which absorbs X-rays. Okay. We are changing the contrast a little bit. We see some X-ray dense deposits on the belly of the animal. I think now we'll come back to the intact animal again. Okay, good. Now if you talk to biologists about woodlice, you can see that they have a mineralized cuticle, obviously. They have a cycle of shedding the cuticle, because in humans or mammals, when we grow, our endoskeleton grows as well. The problem with a crustacean or a woodlouse is when it grows, the exoskeleton becomes too small, it has to shed the old cuticle and to grow a new one. So that's what well, like these animals are all doing, like crabs or these kind of animals. So the problem is, for this animal, it's a land-living organism. And the cuticle is mineralized. It contains a lot of calcium because it's mineralized with calcium carbonate, a small amount of calcium phosphate as well. But it contains a lot of calcium. And land-living organisms have typically a shortage of calcium because, including humans, often we do not eat enough calcium in our food. And the same is true for the woodlouse. There's a lot of calcium which it needs for the cuticle. If it sheds off the cuticle, it has to get a lot of new calcium in very short time. And of course, the animal is unprotected in the time when it has got no cuticle. So it has to gather calcium very rapidly. What it does is, so it undergoes a circle. First, the rear part of the animal is demineralized, at least to some extent. And we have these so-called sternal deposits of calcium carbonate, where some of the calcium carbonate mineral is stored during molting, changing the exocuticle. So more and more. Then this rear part is shed off, and only the front part is mineralized. So you can always see here the animal from the top and from the side as a cut. You can see the sternal deposits. Then we have this phase where the sternal deposits of calcium carbonate are mobilized again to mineralize the rear part of the animal. Then it is shedding off the front part. And so it's a little bit too bright. Can we make it a little bit darker? Darker? Just a little bit, only for this image maybe. Oh, just for this image. Just what I want.
Okay, stay here. Let me know.
Only for this image to show you this red arrow here.
There's a switch. One is working and the other one is badly working. Yeah. I'm sorry, I cannot switch off again. So
okay.
Is it okay?
Fine. Okay. You can see this red dotted arrow. The animal is eating this posterior part of the cuticle, which has shed off, to take advantage of this calcium. So you can find it after this molting period in the stomach of the animal. This is this old part of the cuticle, which we can find here. So it's digested and the calcium is used again. Then the front part of the animal is removed, and then it is mineralized again. So calcium is pumped from the rear part to the front part, and then it's ready to grow, to undergo another cycle. It depends on the species, but this happens every 4 or 5 weeks for normal woodlouse. So in principle, you could find these things in your garden, but in practice, apparently they are eating it immediately, so you're not going to find it. But if you are cultivating them, you may be successful. Well, these sternal deposits, where calcium is stored during molting, in the X-ray scanning electron microscope, they are spherical with a diameter of about 1 micrometer. So these are these objects of calcium carbonate. This is in the X-ray powder refractogram fully X-ray amorphous, so it's amorphous calcium carbonate again, which makes sense, because it's only a temporary storage of calcium. So if it's energetically very high, that means X-ray amorphous calcium carbonate with a high energy compared to calcite with a low energy because it's crystalline. So it makes sense for an intermediate storage to preserve it in a metastable polyamorph in contrast to a crystalline polymorph. So then next we studied the shell or the cuticle of the woodlouse itself. The question was, what is the mineral phase? So it must be mechanically strong for protection. That's the reason for having a cuticle, an exoskeleton. And it must be bioresorbable. It must be decalcified before molding. So what we did was a full chemical and structural analysis of these cuticles. So one thing you can do is thermogravimetry in a thermobalance. That means you are heating up the sample and you're recording the weight as a function of temperature. Then you can see of this species, there's some water, some organic material, which is chitin or something, organic material, chitin mainly. And then you are losing some carbon dioxide because calcium carbonate is decarboxylating to calcium oxide and CO2. And then you can analyze the residue by X-ray diffraction to see what you have. So what we did was a full chemical analysis, including X-ray diffraction on the cuticle itself. If you are adding a crystalline standard, you can determine or compute by Rietveld refinement the weight fraction of calcite and all crystalline material in the cuticle. Okay. And we also did X-ray atomic absorption spectroscopy to determine calcium and magnesium. Well, all the methods we had for structural and chemical analysis. Oops. That's what came out of it. And we have demonstrated this for about 10 different species of woodlice. But these are the most prominent ones, which I would like to show you. So this is the normal woodlouse, Porcellio scarba, which I have shown you before by micro-CT. That's another one, which lives somewhere else, I think in southern Europe. If you are looking on the composition of the cuticle, it's different in these two different species. And we could show this for about 10 different species. So this one has a comparatively high amount of organic matrix. This has a low amount of organic matrix. This has a lot of mineral inside, about 75% of mineral. This has got only 60 or percent of mineral, more organic matrix. So there are some differences in the cuticle composition in these species. And we could correlate this with the biological flight behavior. If you have a woodlouse, if you want to catch it as an enemy, the woodlouse will run away. You know from the garden they can run away very fast. So it avoids predation, being eaten, by running away or clinging to the substrate. If it cannot run away, it will cling to the substrate, and it's a little bit difficult to lift it. For this, it requires a thick but a flexible cuticle, which should not be too heavy because it wants to run away. This one, Armadillidium vulgare, has a different escape behavior. It walks slowly, and it typically avoids predation by rolling itself into a sphere. That's not what our common woodlouse is doing. For this, it requires a very thick and inflexible cuticle. So it makes sense to have a cuticle which is highly mineralized, heavier, but this animal doesn't want to run away, so it just needs a very thick shell for protection. So it makes sense to have a low amount of organic matrix and a high amount of mineral. Chemically, if you look on these cuticles, they always have the same composition: some water, some organic matrix, some crystalline magnesium containing calcite, and you can also compute the amount of magnesium in the calcite by X-ray diffraction. some amorphous calcium carbonate, which is the majority, and amorphous calcium phosphate as well. You cannot see this in the X-ray powder refractogram at the beginning, but after heating to 1000 degrees C, you can see the crystalline hydroxyapatite. So after chemical transformation, crystallization. Okay, next example. This is calcium sulfide hemihydrite in statoliths of Periphylla periphylla. That's a deep sea medusa. That's also a collaboration with colleagues at Hamburg University Zoology. This is a deep sea medusa. It's a little bit more exotic, not the ones which you would find in the North Sea, near Germany or near France. I think it lives in Scandinavian fjords or so. The important thing is that these jellyfish, they have got typically more than one brain. Humans have got only one brain. Jellyfish have 4 brains in each corner of a circle. You have one brain. And in these brains, they also have gravity sensors, which contain some inorganic mineral. That's how this story started. The people from biology approached us and said, well, we have got some inorganic crystals from our deep sea medusa or jellyfish. Could you please analyze these so-called statoliths, which has been known but not chemically analyzed. So some inorganic material which is probably used for gravity sensing. That's what biologists believe. So this is a statolith of Periphylla periphylla, seen from the top, from the side. These are crystals, single crystals, beautiful crystals, with a length of maybe 20 or 30 micrometers, diameter of maybe 10 micrometers. So beautiful single crystals in this animal. So first we did energy dispersive X-ray spectroscopy in the scanning electron microscope, and we found calcium, sulfur and oxygen, which points to calcium sulfate. And as this is a water-living organism, it makes sense to assume that we have gypsum, calcium sulfate dihydrate, which is the normal calcium sulfate phase in water contact. Well, then we made powder diffraction at the synchrotron again, because the amount of material was very small. You can see even a synchrotron powder diffractogram has a very high signal-to-noise ratio, but there's no way around this. With a laboratory diffractometer, you wouldn't see anything. Then you can record an X-ray powder diffractogram, compare it to the known calcium sulfate phases. Even if you look on this as a fingerprint method, you can see it's not gypsum, it's not the dihydrate. It's either basonite or hemihydrite or plaster of Paris or anhydrite, which this is anhydrous calcium sulfate. They have the same crystal structure, except for the water and some channels in the structure. So it's not gypsum, but it's calcium sulfide hemihydrate or anhydrite without water at all. We could determine the unit cell parameters, and they fit very well to hemihydrate of calcium sulfate. Well, the colleagues from crystallography in Hamburg were even able to make a single crystal X-ray structure analysis, again at the synchrotron. So they had a small crystal, but perfect enough to have a single crystal X-ray structure analysis. So they even found the water, oxygen in the channels along the C-axis. So it's really the structure of calcium sulfide hemihydrite, including the water. They couldn't even find the water. So these are the parameters for the structure analysis. So it really worked very well. And it's a direct proof that we have calcium sulfide hemihydrate in single crystalline form in the statoliths of these deep sea medusa. Now, then you can again come back to chemistry. The problem is, if you argue from a chemical point of view, calcium sulfide hemihydrate, so-called plaster of Paris, by the way, it cannot be crystallized from water. That's why gypsum, the dihydrate, is typically heated in autoclaves to about 105 degrees C to get the hemihydrate, which is a white powder, and you can mix it again with water, and then you have this gypsum for modeling, for buildings or for the doctor and so on. So you cannot crystallize this from water. Thermodynamically, it's always metastable compared to the dihydrate, to gypsum and to anhydrite. So it's a metastable compound. You can precipitate it from water, but only under very exotic conditions. from saturated calcium chloride solution, which has a lot of salt, or from magnesium sulfate solution, which is very, very salty, far away from seawater. Under these conditions, the hemihydrate should react with water to dihydrate. We conclude that it is stabilized by the biological system because we found it in the living organism directly taken from water. And the mechanism of formation is unknown, but one idea could be that the water activity is reduced in the presence of protein to crystallize hemihydrate in water, from water, which is not possible in pure water, but it's possible at high salt concentration by reducing the water activity. So maybe this is possible in some compartment, or obviously it's possible, maybe in the presence of proteins or some other biomolecules, but that's what we do not know. Well, we studied this in another number of other species. These are different statoliths, always single crystalline, smaller and larger, but always calcium sulfide hemihydrate. If you talk to biologists, you can even talk about some taxonomic issues, because jellyfish, they're also a very old and successful species on Earth, and they're more or less related. And the biologists are arguing about the relationship between all these different species. Where do they come from? Where is this how is this taxonomic tree true or correct or not? And the nature of the biomineral may help the biologists to put all these species into the correct place of this tree. Well, we also did micro-CT. So it's not only one crystal in these statoliths, it's an organ with several hundreds or so of these single crystals. So a whole bunch. Then you can analyze this, make cuts, and look on the size. They are not all the same size and shape and so on. So this is the whole organ, and this was just one single crystal so far. Well, the reason why these animals are using calcium sulfide hemihydrate with some efforts, apparently, at least chemically, it must be considered quite an effort to have calcium sulfide hemihydrate from water. Maybe the reason is the density of the dihydrate is 2.31 grams per square centimeter. The hemihydrate has a higher density because it has got a lower water content. You have to correct for buoyancy, that means -1 in water. And then the density ratio is 1.73 to 1.31. So the density of the hemihydrate is about 32% higher in water. And maybe this is the reason for using hemihydrate as gravity sensor. Yeah, that's just speculation, but it sounds reasonable at least. Okay. Next part is about shark teeth. That's one project we started about 3 years ago. Was just started as a small project and turned out to be a very interesting and large project with very interesting questions and answers. This is a project together with people from the Max Planck Institute for Iron Research, Professor Rabe, Dr. Fabricius, who work in Düsseldorf, nearby our university at the Max Planck Institute. So we analyzed shark teeth. Of course, you know, all know sharks. Sharks are, again, a very successful species on Earth, living on Earth since 300 million years or so, since a very long time, in many cases almost unchanged. And first we had these two sharks, or the teeth of these sharks, for analysis. Sharks have a different jaw than we have as humans. They are changing their teeth all the time, every other months or so, depending on the species. And they have a so-called revolving jaw. That means the new teeth are forming here and coming out when they are needed, and the old ones are shed off. That's why you can find shark teeth in the sediments. They are not very expensive. You can also find many fossilized shark teeth because they were just found in the sediment. So it's not difficult to get these samples. It's more difficult to get them analyzed from biology, but that's what we did together with people from biology for taxonomy of the shark teeth. So they have plenty of teeth coming out all the time for these two species. And from the chemical point of view, or biomineralization point of view, the interesting question was, you all know probably that human teeth consist of hydroxyapatite. That's our teeth, our bone, they're all hydroxyapatite. Sharks are the only species which is using fluoroapatite for their teeth. This is known since decades. We are not the first ones to find this out, but we were the first ones to have a closer look on these samples with high-end methods. So that was our idea, to study these shark teeth, first in terms of morphology, what is their setup, and second in terms of their hardness. Before we did this study, I kept telling the students or other people during lectures that sharks have teeth of fluoroapatite, because fluoroapatite is harder than hydroxyapatite. If you are taking the pure mineral, you can measure the hardness, and fluoroapatite is a little bit harder than hydroxyapatite. And I kept telling people, well, sharks need harder teeth because they are preying more than humans, so that's why their teeth consist of fluoroapatite. So that was our idea why we started this whole set of experiments. So these are two shark teeth from mako shark and tiger shark. This is a geological fluoroapatite crystal which we analyzed for comparison. It has some color because of incorporated transition metals, but it's chemically almost 100% fluoroapatite. Well, first thing was X-ray diffraction on a lab instrument, Doppler synchrotron. You can see enameloid. In sharks it's called not enamel but enameloid because it's a little bit different. But what we can see here is dentin inside of the teeth and enameloid outside of the teeth. That enameloid is highly crystalline, which you can see due to the sharp peaks. We can compute by Rietveld refinement the crystallite size. The dentin has broader peaks because it consists of smaller crystals, well, like in bone more or less. If you make an X-ray powder refractogram of bone, you will have an image like this approximately. It's all apatite, even fluoroapatite we could show by crystallography. There are no other phases. So enameloid large crystals, dentin small crystals, as in our teeth. Then you can do thermogravimetry. You can determine the mineral content and the organic matrix content. This is enameloid, this is dentin for these two species. Enameloid is highly mineralized. It contains only a few % of organic matrix. The rest is fluoroapatite, 90+%. The dentin contains maybe 20% of soft matter and 80% of mineral. It's a little bit depending on the species, but it's more or less like human teeth. Enamel, very highly mineralized, a very small amount of organic matrix. Dentin, more like bone, nanocrystals of apatite and a high content of organic matrix. In bone it's about 50-50. In these teeth it's about 80-20 from inorganic to organic part of the dentin. Well, if we look into a morphology, this can be done by cutting these teeth and making scanning electron micrographs from all different orientations. So you need many images to get results to know how the ultrastructure looks like. What you can see here, this is the tooth surface. There's a so-called shiny layer which consists of more or less disordered irregular crystals. Then we have crystallite bundles going from here to there, from left to right, from up to down, from front to back. So after making many images and analyzing them, many cuts and fractures, we found that this model should be correct. We have a shiny layer, randomly oriented crystals at the outside. We have crystallite bundles in all three geometric directions, which are intertwined and probably giving the teeth their high mechanical properties, so toughness and hardness together, like in human teeth, more or less. Well, here another image. So we have circumferential bundles, radial bundles, and axial bundles, and the shiny layer. So that's the enamel structure of shark teeth. And for all these species of sharks, they all had more or less the same structure. So there was no difference between the species. If you look on the cut by scanning electron microscopy, again you see the enameloid layer and the dentin inside. This is just the tip of the tooth. Going into higher magnification, you see some dentin-enamel junction, as in human teeth, where the almost purely inorganic phase starts to become intertwined with the more organic dentin. If you are doing first EDX and then really elemental analysis, you find that fluoroapatite is only present in the enameloid, at least if you go from stoichiometry. So the stoichiometry for fluoroapatite is 3.64 weight% of fluoride. That's what we found in the geological fluoroapatite crystals, 3.6 weight% fluoride. In the animaloid, we have 3.1 weight%, so almost stoichiometric, but the dentin apparently does not contain fluoroapatite, but hydroxyapatite, maybe with some fluoride inside. These numbers are not too accurate because it's very difficult to separate these layers quantitatively. You are never sure whether you have only 100% animaloid or 100% dentin. Especially for animaloid, we are not quite sure about some contaminations from dentin. But it's clear, and we found this in all our investigations, including EDX line scans. In the dentin, there's a small amount of fluoride, and the animaloid is almost quantitatively fluoroapatite. So it's not true that shark teeth consist completely out of fluoroapatite 100%, only the animaloid, only the outer part. Okay, well, and then we did mechanical studies together with the colleagues from the Max Planck Institute, micro-indentation and nano-indentation on different orientations of the teeth, on animaloid and on dentin and so on. And the surprising result was nano-indentation and micro-hardness for dentin and animaloid. For shark teeth, you get some numbers, and if you can compare it to human teeth, and you find within the error of magnitude of error the same hardness for human teeth and shark teeth. That means our teeth are as hard as shark teeth, despite the fact that they contain hydroxyapatite, which is not as hard as fluoroapatite. Yeah. So we published this in 2012 in the Journal of Structural Biology, which is a decent journal. But we were approached, somebody read it from the Discovery Channel. I think Thibaut knows this story. From Discovery Channel, so they founded sharks. They're scanning the literature about sharks or some buzzwords. So they reviewed our article in a more or less scientific way. And the first message was that first, sharks have built-in toothpaste because we are all using fluoride in our toothpaste to make the teeth harder. So shark teeth consist of fluoroapatite, so they have built-in toothpaste. That was the headline. And this really made itself around the world, so we could follow it in a few days. So this was taken from Discovery Channel in all more or less distorted ways. The second message was that shark teeth are not harder as human teeth, so we can bite back if a shark is biting us. So that was a quite exciting experience. I never had so much popularity among normal tabloids and newspapers. So if you want to have publicity, go to something which is interesting for the public, like sharks. Yeah, it was really an experience. Well, scientifically, that was really interesting. But that means that the human teeth are able to make up for the less hard mineral by better organization, at least relatively, compared to sharks. Well, you can then study the hierarchical organization of shark teeth, starting from fluoroapatite, the elementary unit, crystallites, bundles of crystallites, different bundles, different layers, and so on, including the organic matrix, which typically is surrounding these individual crystallites and bundles. We didn't analyze this in more detail, but we could see it by selective etching of the mineral. Then you see how the organic matrix remains, well, like in mollusk shells or teeth, by etching. Well, after having studied shark teeth, we were looking for something else to repeat this Discovery Channel experience, maybe. So the next idea was crocodile teeth, which were not studied so far. So we organized some teeth of crocodiles. That's a normal saltwater crocodile. Crocodiles are also shedding off their teeth after a while, unlike humans, but they have a different way of shedding or replacing them than sharks. Crocodile tooth is hollow, and the new tooth grows inside the old one. Therefore, when the old one is shed off, the new one is already almost there. So it grows from the inside. It's a completely different mechanism of replacement. If you are looking with the same techniques on crocodile teeth, dentin, enamel, cementum, which is the outer part of the tooth, interestingly, it's all more or less nanocrystalline, even in the enamel. It's a little bit more crystalline, but not very much. So they don't have a very highly ordered structure, which we then analyzed further by synchrotron micro CT. This is a crocodile tooth. You can see the dentin, and here this cap, only the white one is the enamel. The thickness of the enamel is very, very low, a couple of 100 micrometers, which is much less than a human tooth. In our teeth, the thickness may be up to 5 millimeters depending on the tooth, but more of the order of a millimeter as a rule of thumb. So the enamel of a crocodile tooth is very, very thin. Here you can see it again. Then we did some micro CT line scans about the density. Then you can see the X-ray density of enamel, dentin, enamel. So like this line scan, or here cementum, dentin, hollow inside, dentin again. And then you can distinguish the phases and their mineralization by the grayscales. We did thermogravimetry, which I'm not going to show you here. And then we did again microhardness tests, and it's again the same order of magnitude than human teeth and shark teeth. So all these teeth we have investigated so far have the same mechanical properties in terms of hardness. This is geological hydroxyapatite, which is harder, of course, like fluoroapatite if it's from geology, but it's not tough. I think that's what you all know from biomineralization. Minerals only have their good mechanical properties because we have this organic matrix inside. The pure minerals are much harder, but also much more brittle. Okay, then we did some thought about biology. Why crocodile teeth are different from human teeth. Crocodiles are not chewing, they're just gripping and securing their prey. So they're just closing the mouth and gripping the prey. They don't need a thick enamel layer because they're not chewing. In case two teeth should hit or hit a hard part of the prey, they would fracture if they would be highly mineralized. So maybe they have a tooth which is less mineralized, more elastic, a lot of dentin, only a small amount of enamel to overcome the impact of the force if it hits a very hard part of the prey, like another bone or another tooth. That's an idea. That's how a crocodile looks like. And if the tooth is damaged, it will be replaced by a new one. Okay, the final part, just a few slides, about fishbone. I've seen some posters about fishbone as well here at this conference. This is normal mammalian bone, which you all know. We made a small study on fish bone. Up until this time, I always thought that fish bone is not mineralized because if you are eating a fish, it doesn't look very mineralized. It looks like organic material. If you have a fish bone, it looks like pure organics, because not very hard. But if you are making an analysis of fish bone, it's really hydroxyapatite, nanocrystals, and organic matter, and so on. So it's almost impossible to distinguish fish bone from mammalian bone just on chemical techniques like X-ray diffraction or thermogravimetry. And one thing we did with micro CT, we took a zebrafish, and that was an experiment. At this time, it was the largest object which the people at the synchrotron had in one scan. That's a whole zebrafish with a length of maybe 2 centimeters. It was embedded into resin, so the soft tissue is still there, still present. It had to be cut for reconstruction. It was not mechanically cut for the experiment. It was just cut for reconstruction of the data set and then reassembled again. And then we can have a look on the whole zebrafish, and you see how it is mineralized, like human bone. And we can see the teeth back in the throat of the zebrafish. And then we go along the spinal cord, which is hollow. Yeah, here it comes again. And then we got other samples from Professor Görlich from Aachen, who had Medaka fish, which is another model organism in fish biology. There's zebrafish, and Medaka is another standard object. He had wild-type fish and mutant fish, which had some distorted spinal cord. So we had made micro CT of these two fish, wild-type, normal Medaka, and mutant with this distorted spinal cord. then we could have a close look on the distortion in the micro CT. Yeah. So, okay, now I would like to come to my conclusions. So these results were assembled in the last 10 years or so, always together with people from biology. As a chemist, you can apply structure-sensitive high-end techniques, interpret the results, but you always need some people from the biosciences to give you good samples to help you to characterize your samples, to get snail embryos or wood lice, or to taxonomically analyze your shark teeth. Otherwise, you will have a problem interpreting your data. But that's what we have learned in the last 10 years. It's very promising if you have high-end chemical and physicochemical tools to apply them to biological systems together with people from biology. So with this, I would like to end. I thank the co-workers. I thank you for your attention. Thank you.